Okay, we're going to do our last topic in this unit. So we're going to look at what we call Newton's method. It's another application of derivatives, but it doesn't deal with the related rates and volumes and areas and things like that that we did in the previous topics. This one, what Newton tried to do is figure out a way to calculate the solutions to an equation or the roots or factors or whatever you want to call it for any kind of function that doesn't factor nicely. So we know if I gave you an equation like y equals x squared minus 4, we know that we could factor that into plus 2 and minus 2, and those would give us the location of our x-intercepts. So our quadratic would look something like that, and we know that we'd have an x-intercept at -2 and +2. So that works really well when a quadratic factors. If it doesn't factor, in Math 20, you might remember you did things like quadratic formula or some other strategy to try to get those decimal or square root answers. So that works well for quadratics. But what Newton was trying to figure out is, can we do this for a cubic, a fourth degree, a sine function, a log function, any other kind of equation that has x-intercepts, would we be able to solve them? So his idea is, and remember, this came before the time of calculators, so it's not simply just graph it on your calculator and find it that way. This was all done by hand, no calculators, and he was able to figure out a way to get these x-intercepts accurate to 10 decimal places or more. It doesn't really matter what we stop our accuracy at. So what his method does is, it's an estimation procedure where we take a possible x-intercept and we plug it into a formula to get a more accurate one, and then we just keep repeating that over and over again to get a better and better answer. Often computer programs use this to solve things. So for example, on your TI calculator, there's a solver button under the math function, and that's what it uses. It actually uses Newton's formula to do the solver. So it'll ask you to sort of make a guess or an estimate of an x-intercept, and then it takes that answer and does a whole bunch of calculations repeatedly to get the correct, accurate answer. So how his formula works is, we need an x value to start with, we need the equation, and we need the first derivative. And then we just do a series of calculations to get the roots more and more accurate over time. So let's look at this picture. This would be a good way to sort of estimate what's going on. So for this scenario, Newton's formula is at the top here, and we'll talk about it more in a second. But basically how he came up with it is, he said, if we take a function, and let's use one that we already know. So let's suppose our red graph in this case is y equals x squared minus 4, and this is only a portion of it. So if we zoom in, we would know that that x-intercept is at 2. Okay, so what we're going to do is use his formula to see if we can get an answer of 2 that we already know it is, but let's assume we didn't know it was 2. So what we're going to do is, we're going to take our formula that we have for Newton's and go from there. So if you look at the picture, what he does to get the formula is, we need to figure out an estimate to start with. So let's suppose we put 2.5. So let's suppose the starting guess was 2.5. So that would be, if we plug 2.5 into our original equation, that would give us our y value. So what Newton figured out is, if we take that y value and we divide it by the slope, so you can see the way it is here, the blue line is our tangent line slope. If we divide those two and subtract it from our 2.5, that'll give us the location of where that tangent line is going to cross the x-axis. And you can see in this case it's quite a bit closer. So let's actually do this calculation. So we're going to put in 2.5. So we're going to solve, let's call it x1 is 2.5. So now we're going to try to figure out what x2 is. So you'd put in 2.5. We would plug 2.5 into the original equation. So that'd be 2.5 squared minus 4. And then we're going to divide that by the derivative. So our derivative equation would just be 2x. So we're going to divide that by 2 times 2.5. And we just crunch that out on our calculator and see what we get. So if we put in 2.5 minus the top, divided by the bottom, we get an answer of 2.05. So you can see that that x location is quite a bit closer to our 2 that we know that the actual answer is going to be. So now what Newton figures out is, well, that just gave us a better location, so now we're going to use the green line. So we're going to do the same process over again, but we're going to start with 2.05, and we're going to take that y coordinate of the green line divided by the slope of the green line, and that should give us even a more accurate answer. So we repeat this calculation with 2.05, and we plug that in our calculator and see what we get. So this time, when I plug all that in, I'm getting 2.0006. So you can see we're almost at the correct value already. And you can see in the picture, that's pretty close. That green intersection point is pretty close to our original red dot of 2. So if we wanted to, we could try it again. I won't bother, but you can see we're getting closer and closer. If we tried it again with 2.006 and we plug all that into our formula, it's going to get us closer and closer to 2 by the time we do it. So that's how Newton's formula works. It's just a series of substitutions and estimations to try to get the answer more and more accurate. So our process that we're going to do is, right, we knew the last question the answer was 2, but we're not always going to get that. Quite often we're going to get decimal roots. So our process is, you're going to be given an equation. We often will also be given a starting point, or our x1 value, but not always. Sometimes you have to estimate it yourself. But in this case, I'm giving you the equation. Our first step is find the derivative. So in this case, our derivative would be 3x squared minus 2. And then the second step is we need that x value, or be given that x value. So in this case, let's suppose we're going to start at a value of 2. And the only reason I'm giving you 2 is this graph looks something like that, and we can see that the x-intercept is slightly bigger than 2. So just from that graphing the original, we can get a pretty good estimate if we need to have that starting value. And then after that, we just plug it in the formula. So we're going to use 2, and we're going to subtract 2 into the original equation, and divide that by 2 into the derivative equation. So we're just plugging 2 into all of those x locations. That'll give us our new answer, and then we repeat that. So on this page I have the calculations. You can see there was our original equation, this was our derivative, and we're using 2 as our starting point. So you can see the first step is I plug 2 everywhere into the equation, and we're getting an answer of 2.2. So now the next step is repeat it with 2.2, and that should give us a better answer. So this third calculation, you can see now I have 2.2 in all of the x locations, and we're getting an answer of 2.18. Do it one more time with 2.18, and you can see we're getting pretty accurate at this point. So our final answer of 2.17998 gives you even a better answer. Okay, so at this point, if we're wanting to round it to the nearest hundredth of a decimal place, we can safely assume 2.18 is correct. We don't need to go any further. If we wanted it more accurately, we wanted to near 6 decimal places, then obviously just keep going another couple of times until the decimals don't change anymore. If you start further away, so for example, if we started at an x of 3, we'd still get to this answer, it would just take a bit longer. So the first few calculations might jump around a little bit. So we might start at 3, then maybe it goes down to 2.4, then it goes down to 2.3, then it'll go down to 2.2, and then away we go. Or sometimes it'll go from 3, and it'll jump down to 1, then it'll go to 2.5, then it'll go to 1.8, and then kind of back and forth until you get to the sort of the closer location. So the further you start, the bigger that slope line is away, so obviously it's going to take a bit more time to get it narrowed down. So if you have to start with a guess, if you're not given the initial point, I would just graph the original. By looking at the graph, you can kind of get a pretty good estimate of what the x value would be. And if you end up having a graph that has more than one root, so the last one I had was a cubic equation, but we only had one, but technically we could get a cubic equation that has 3, And in this case, if you had more than one, just estimate each one. So let's suppose we can see that, let's suppose this point was somewhere in there, then maybe we would start at negative 2.5. And maybe this other one we'd use negative 0.5. And then maybe this third one we would pick positive 3.5 or whatever. So just pick whatever values look pretty accurate on your calculator, and then from there you should be good to plug those in. So if you do have more than one, we just do the process for each one. So you'd start with negative 2.5, do it a few times to get that one narrowed down. Then start over with negative 0.5 and repeat over and over again until you have all three x-intercepts. I'll show you in class, or I did show you in class, that you can use the storing feature on your calculator, and that'll help do these repeated calculations a little bit more efficiently. I won't show it on here because it's too hard to describe how to do it. So if you know how to do the storing, that would definitely help speed things up. So let's try another example. So this one is a trig equation. So again, if you wanted to graph it first, you could, and it's always not a bad idea anyway, because then you could see how accurate your calculation is. You could use it as a check. So if you graph 4 sine x squared and subtract 2, let's put that in. We can see the graph looks like a normal kind of sine graph, just it's being squared, it's slightly different, but you can still see it's pretty straightforward. So the graph is doing something like this. So we can see that we have multiple x-intercepts. So in this case, I'm just saying use an x of 1, because we can see my graph isn't very good, but you can see this first one is pretty close to 1. So 1 radian, remember we're always in radians for this stuff, for calculus. So with a radian of 1, we can see that we're pretty close. It looks like it's just a bit under or a little bit over one or the other. But the idea is we're just going to find one x-intercept. Obviously, being a trig value, we've got infinite numbers. So usually you'll get a restricted domain or something where it'll only ask for a specific number of them. So let's do this question with 1. So we're going to use our x1 of 1. Our original equation is 4 sine squared minus 2, so the other thing we need is our derivative. So in this case, because it's sine squared, we got to remember our chain rule. So we'd bring the 2 down, which would make it 8, drop our power to the 1, and then times it by the derivative of the brackets, which in this case would be cosine. So we should have 4 sine squared minus 2, and then our derivative would be 8 sine x cos x. So now we're good to go. So in our formula, if x1 is 1, we're ready to solve for x2. So x2 would be 1 minus 4 sine squared of 1, and then we would divide by 8 sine 1 cos 1. And again, you can type those in your calculator. We could do storing, whatever method you want. So I'll type it in here quick and we'll see what we get. So we get 4 sine 1 squared minus 2, and let's divide that by 8 sine 1 cos 1. Make sure you close off your brackets, otherwise your calculator will give you an error. And I got an error. Let's see what happens here. Oops, my calculator's not working very good. Okay, so when I do that calculation, I get 0.77117. So now let's do another quick one. So now we're going to plug that decimal in for the 1 location. So we'll do that quickly on the calculator. So when I type that in, I'm getting 0.7854. So you can see it's pretty close. We're already near that right spot. So let's just stop there. I think that's close enough. And remember, these are in radians. So if we wanted to, we could convert it to degrees if you wanted to figure out what that is in degrees. So if we times that by 180 and divide by pi, we get 45 degrees. So it looks like that would be at 45 degrees in terms of the graph, and we could see that algebraically we would have been able to solve it for that 45 degrees, right? If we take this equation, bring the 2 to the other side, divide by 4 gives us a half, and we could square root that. So square root of a half would be the same thing as 1 over root 2, and if you remember from the unit circle, sine and cosine are 1 over root 2 at 45 degrees, so that definitely seems correct in this case. All right, let's do one more example. So this one has a more complicated equation, so we're going to take care of that. And once we draw the graph, I think there's going to be multiple roots. So I actually want you to solve for all of the roots, not just one in this case. And we don't know what to start with, so we're going to have to figure that out as well. So the first step, what I would do is let's rearrange the equation. So let's rewrite it as... Actually, we don't need the y. We'll just make it equal to 0, right? Because we're solving for roots, so we need these to be 0. So let's rearrange the equation. So we'd have x squared minus 3 take away 1 over x minus 2 equal to 0. And let's simplify that a little bit more. Let's write it as a negative power. Let's write it as x minus 2 to the negative 1. So that'll make it a little bit simpler. So that'll be our starting equation. And if we do our derivative of that, so our derivative should be 2x. Derivative of 3 is 0, so we don't have to worry about that. And if we do the chain rule on the brackets, we get plus x minus 2 to the negative 2 times 1, which does nothing. So that should be it. So there's our two functions. So now we need to figure out what we're going to start with. So again, I would put this on your calculator to get a pretty good idea what it's going to look like. So let's graph the x squared minus 3, and then let's subtract the 1 divided by x minus 2 part to graph it. And let's see what it looks like. So we get sort of a quadratic type of shape, and then we get the asymptote line at 2, which we already know that seems to make sense. And then we get another curve. So it looks like from my calculator screen, we're getting sort of a graph that looks like this. So now the idea is we just need to figure out those three. We have 3 x-intercepts, so it's good to see how many there are, and we need to estimate what they are. So from the first one from left to right, it looks like this one's around negative 1.5. So we're going to start with negative 1.5 for our first one. The second one looks like it's a little bit less in the positive direction, so maybe about 1.4, 1.3, something like that. Let's try 1.4 for the middle one. And the last one looks like it's 2. Right, it's somewhere in there. So it's maybe 2.4, 2.5, something like that as well. Let's try 2.4. So we have 3 different x-intercepts. They're all decimals. We can see that from the screen without going any more detail. So let's see if we can get this to work using Newton's formula. So we'll plug in negative 1 in the first. I'll write it out the first time, and then we'll just go from the answers from there. So we're going to plug in negative 1.5 into our equations. We'd have negative 1.5 take away. Now the negative 1.5 is going to go in the original, so that'll be negative 1.5 squared minus 3 take away negative 1.5 minus 2 to the negative 1, and we're going to divide all of that by our derivative. So 2 times negative 1.5 plus negative 1.5 minus 2 to the negative 2. Okay, so that's the calculation we're going to do on our calculator, and that'll give us our second approximation. Okay, so when we plug all that in, we get negative 1.659 as our first approximation. So now let's plug that into the same equation. And we get negative 1.651, so we're getting pretty close. I'll try it one more time and see. We're probably close enough at that point. And we get the exact same answer, yeah. So it's negative 6.65109. So if we round it off to 3 decimal places, we're good at that third approximation. So that takes care of the first one. So this first one then here we can see is negative 1.651. So let's repeat it with our second one. So like I said, we're going to use 1.4 as our starting point. So in this case, I'm going to do the storing feature just to make it a little bit quicker. So if I store the 1.4 and redo our calculation, our x2 ends up being 1.287. So it's a little bit smaller. Let's repeat it with that value. And I get 1.274, so we're getting pretty close. So let's try it one more time. So you can see, it looks like my estimate of 1.4 was a little bit too big. It was closer to 1.3, but it doesn't matter. We're getting there eventually. So if I do it one more time, we should be good. We're getting 1.2738. So you can see if we round it off to 3 decimal places again, it would be the 1.274. So that's our second one in the graph. So the third one, we said let's estimate it at approximately 2.4. So we'll do that one as well. And plug that 2.4 into the original equation. We get 2.378, so it looks like we're pretty close right off the start, or 2.376. So we'll try it one more time with that answer. And I'm getting 2.377. So I think we're good there. You could try it one more time, but it should round off to that same value. So that one we were pretty close right off the start at 2.4. So 2.377 ends up being that third x-intercept. And that's it. So you can see Newton's formula works pretty good. If you start with a pretty close estimate, it won't take too many steps to get the accurate answer. Obviously, if we started further away, like this last one, if I had plugged in a 5, it would have taken us a lot more steps to narrow it down to that 2.377. So it doesn't matter what type of equation, could be a sine, a log, polynomial, rational like we just had, all functions will work. If you have more than one x-intercept, just repeat the process for each one, and that's it for Newton's method.